Good morning.
Good morning.
So today's topic will be the traditional AC generator. This topic is not in the textbook, it's external topic. And I would like to include it because to complete the overview or to complete the image about the power system, we talked about the transformer, the transmission lines, the loads, the power factor correction, the US residential load, all of this stuff. Then how about talking about the generators, how the generation will be. We talked about the sources last lecture, and there are several types of energy using photovoltaics, using renewable energy sources, wind energy, coal, fossil fuels, etc. So in today's topic will be about the traditional AC generator, and the generator and the motor are very similar, but depending on am I converting the mechanical energy to electrical energy or the vice versa. After today's lecture, I encourage you to go to worksheet 12 because it tells you about the procedure that we need to do to solve the circuit of traditional AC generator. So again, this is additional notes. This is not in the textbook. Before starting the generators, let's talk overview about the electrical machine. So the electrical machines has two classifications. It can be either static machine or dynamic machine. So the static machine, no moving parts. Machine that's running and there is no moving parts in it. While dynamic, it has moving parts. So one example of the static machine that there is no moving part, which is the transformer. The transformers transfer the voltages from one type to other type we don't have any moving part, there's no motion. While the dynamics or the moving parts, it can be motor that's rotating or moving. It can be generator, it's also moving. It can be something called exciter. It's also have moving parts. The motion can be classified also into two parts. It can be linear motion. It can be rotated motion. The vast majority that we know about the motors or generators are rotating motion. But there are some can be linear motion. For example, sometimes the electric train, it can be one part of the electric train, like there is a magnet, here is north, here is south, and the electric train in the middle. So sometimes this electric train can be hanging out, it's in the middle, so there is nothing here and nothing here, so nothing to catch the train, just the magnets. Then the motion going this way. If there is electrical current flowing, then the motion will go this way. So this is one example of it. Also some other part of examples in industry, in factories. So some machines, for example, to close the lids, machine goes up, down, up, down. So for example, if there are lids of the water bottles or lids of cans, then goes up or down to close the lid, then up. Then the machine is rotating and so on, is moving. So there are several types of linear motion, but we will focus on rotating because the vast majority of the machines are rotating. So electrical machines, again, can be static, dynamics, like transformer, motors, generator, and exciter. So how is this motion being produced? Why it's rotating? Why it's moving? What's producing moving? Let's recall Faraday's law. Faraday's law has three conditions. First thing, which is moving parts, then magnetic field, then electrical currents. Electrical currents. So Faraday's law says that all conditions must be met together. What does this mean? If I have any two of these conditions, the third one must exist. If I have moving parts and magnetic field, this should produce electrical currents. When I have magnetic field and electrical currents, this should produce moving parts. The moving parts, sometimes we can say it's mechanical energy. Electrical current, it can be electrical energy. Magnetic field, it can be, for example, a magnet. Or anything else. So based on that, we can say whenever we have a magnetic field plus moving parts, this must produce electrical currents. Whenever I have magnetic field plus electrical currents, this must produce moving parts. So whenever I have magnetic field plus, in other words, mechanical energy, whenever I have here magnetic field plus electrical energy, this produce here is electrical, this produce mechanical. So when there is a magnetic field and moving parts, this produce electrical energy. This is the idea of Watts, or the principle of Watts. Yes, but what does this conversion mean? This can be used in which device? Motor or generator? This generator. I have mechanical energy, converting the mechanical energy to electrical energy. This is motor, a generator, right? Yeah. So this is the principle of generator. When I have magnetic field and electrical currents, this is the principle of motor. That's it. Here's the justification. So we can realize that whenever I have mechanical energy plus magnetic field, I can produce motor. But let's think also more about it. What's the common factor between these two? Magnetic field, right. So the magnetic field matters, which means when I have only moving parts, there is no way to produce energy. I need to have a magnetic field to produce currents. Otherwise, there is no way. So the moving parts can happen everywhere. But I cannot produce energy because I need to have a generator. And the structure of that generator, there should be a magnetic field inside it. Then I can produce energy. And the same for the motor. Whenever there is a current, this does not mean there is a moving. The currents are everywhere. The currents are in power lines, but we don't see any moving because there is no magnetic field. When there is a magnetic field, then a moving part can be had, or a moving can happen. Okay, clear? So this is the principle of Faraday's law. I'm making it for you just to make sure that you understand the idea. So of course, it's way more complicated than that, but I try to simplify it as simple as possible so it can be understandable for everyone. Someone can say, how about when I have electrical currents and moving parts? What will happen? Faraday's law, all of these three conditions must meet. Let's see, when I have electrical currents plus moving parts, do you think this will produce magnetic field? Yes, this will produce magnetic field. And this thing is called exciter. This is used in some part of motors, some part of generators, because some structure of these generators does not have a magnet inside. So we need to reduce a magnetic field to, to have a motor or generator action. Then we need to use exciter, which is we are using the moving parts and we have something to supply the moving parts, so then we can create exciter, or we can produce a magnetic field. It's not only an exciter, it can be applied everywhere in physics. Okay, clear? So, again, having electrical currents alone, even you have electrical currents with wires with multiple movable parts, but without having any magnetic field, there is no way to make a motor. Having only, or when you have only moving parts, or there is a motion, when you have a motion, and you have wires, this will not produce electricity. You need to have a magnetic field. So the magnetic field here is matters. Okay? So today's topic, we will focus on the generator, rotating motion. The generator action, which is basically converting mechanical energy plus magnetic field to electrical energy. Here is the generator. So for the generator, we have multiple types. We have single-phase generator, three-phase generator. Even for the generator, it can be different parts depending on the structure of the generator. Do I have a magnet inside, or do I have exciter? So there are many things about it. But here in this course, or in this lecture, it's called the traditional AC generator. We will talk about traditional. So traditional, what's used for the utility, and it's three-phase. And the type is called synchronous generator. So here for the generator, it can be single-phase or three-phase. And they can be also synchronous or induction. And they can be as well different phase, or different thing depending on, does it have a magnet inside or exciter, something like that. So we will focus here on three-phase, synchronous, and has a magnet inside. So this is a very special case. While like the other type of motors, there is a special course in electrical engineering curriculum. It's called electrical machines. In that course, they have many types. They have single-phase transformer, three-phase transformer, bi-phase transformer. They have also single-phase generator, three-phase generator, depending on different types, DC generator, AC generator, synchronous induction. So it's a very complicated topic. But here I'm going to talk about only a special case. This is how the traditional generator looks like. It's very large size here. This used to generate a large amount of power to supply maybe a city. And there is also one type, or there's another type of the generator, old generator. It can be found at the entrance of Brown Hall. You can find it in the ground floor. Yes, you can find it when you enter using the other side. So that's a special type of small generator. But this one is what is used right now. So this is called three-phase synchronous generator, AC synchronous generator. So all of this, it has many many parts on it, how to control the generation. But the principle, the working principle, there is a moving part based on turbine or based on gas, etc. And based on many things, but there is a turbine producing a moving. And that moving will produce the mechanical energy. Then that mechanical energy, and we have a magnet inside, will produce electrical currents according to Faraday's law. Talking about the generator will take very long time. It might take a course if we want to talk about everything inside the generator. But I want to focus only in the electrical parts, on the working principle. So all of this generator can be modeled to be an equivalent circuit. So that's why we talked about electrical circuit analysis maybe for 1 or 2 months, how to make several analysis. So now we can apply what we have learned before. So we can make this as a shortcut, produce or take the important part or the electrical important parts to make an equivalent circuit. Then we can find, for example, what's the amount of power that we need to generate, or what's the voltages, and so on. So we can make several analyses on that. While, again, when we make this model, it's a very complicated model because it has many structures. But we make this as a shortcut to take only into account the electrical parts. We will not take the physical part. We will not take the humidity or the temperature or the protection if there is overvoltage, if there is something wrong with the frequency. We're not talking about all of this stuff, or how to control these units. We will not talk about this. We'll talk only about what's something important, which is how to produce electricity. Here is in the notes. The traditional AC generator, we will talk about synchronous 3-phase machines. So based on that, we need to know the circuit principles, circuit analysis, KVL, KCL. Since it's AC, we need to know the AC. Then 3-phase, we need to know the 3-phase systems. So you will see it's cumulative application. We need to know everything that we've learned in first and second exam to apply it here. So generator converts mechanical energy to electrical. Motor converts electrical energy to mechanical. So generator, there are 2 parts for these generators. There is something we call it rotor, which is the rotating parts, and there is a stator. So here in this example, the rotor is magnets. The magnets, why the magnet exists? To produce magnetic field. We need to have a magnetic field, otherwise we cannot produce electricity, even if there is a motion. So the magnet will be in the rotating part, so the magnet will keep rotating. Coils will be in stationary parts. Coils are needed because we need to produce electrical currents, so the currents will flow into the coils. So the stator, which is the electricity will be produced, like the rotor, which is rotating, attached to the shafts of the turbine. So the turbine will make the rotor rotates. And the rotor has a magnetic field, then there is a magnetic field inside. This magnetic field will produce, with the moving, will produce electricity into the stator. Now the stator will have electrical currents, will go to the load, or will go to the power, will go to the grid, to the utility. And that's it. So I'm trying to simplify again as simple as possible. It can be more complicated than that, but this is the simplest way. We will not go to very complicated because we are in fundamentals of electrical engineering, so not electrical machine course. Because it's 3-phase, coils are separated 120 degrees. According to Faraday's law, the time derivative of the flux linkage is sinusoidal. Therefore, the voltage being produced is sinusoidal. Also, we can say something here important, which is 60 hertz. What does this mean according to this generator? 60 hertz means 60 revolution per second. Or in other words, we call RPS. We used to talk about the speed or convert the speed to be RPM. This is what makes sense for us. So which means for 60 hertz, it provide us 3,600 RPM. So how did I find it? Which is basically we can say RPM equals to the frequency times 60. Then 60 times 60, 3,600. How about in Europe, if the frequency was 50 hertz, will be 50 times 60, will be 3,000 RPM. So it's depending on how is the frequency operation of the grid, if the frequency 60 hertz or 50 hertz. Therefore, we can see that if there is something wrong with the frequency, this will matters into the speed of this generator. And we talked about the frequency last lecture, depending on the load. If the load is too high, then the frequency will be high. Then the speed of the generator will be higher than what's supposed to be. If the load is too low, or I think the vice versa. If the load is too low, the frequency will be high. Then the speed will be high. If the load is high, the frequency will be low. Then the speed will get low. So, RPM, the speed in RPM equals to the frequency times 60. So you need to know this rule. Here, how many turns do we have, or how many, look at the magnetic field here. The magnetic field produced based on the stator, or rotor. The rotor, we have only one magnet, or one pole pair, or one, we'll call it two pole pairs. Two poles, I'm sorry. We have two poles, which is north and south, right? Because we have only one magnet. Is there any way to have multiple magnets or more than one magnet? Yes. This one. This one, we have two magnets. How many poles? 1, 2, 3, 4. We have 4 poles. So in this case, what's happening here? Well, since we have 4 poles, then we have 2 north, 2 south. Then, by looking here at this one, in order to complete full cycle, how many north do we have and south? Only one, right? So here, north. Let's start from point A and complete one rotation to go back to 1A. So it takes only one magnetic cycle to complete it, right? Which is going from north to south, takes 360 degrees. Right? I'm sorry, north to south to north, to back to north. Right? While here, if I want to go 360 degrees, I will go from north, south, north, south. In 360 degrees, I'm taking north to south, to north, to south, to north. Because every 90 degrees, or every certain period, certain degrees, which is I think 60 degrees, it will be changed. I'm not sure, 60 degrees, 360 divided by 4, 180, 90 degrees, yes. Every 90 degrees, the poles are changing. It's not like here, every 180 degrees, the poles are changing. So we see that it can matters here to complete one rotation. In order to have one rotation, one physical rotation, it will take 2 magnetic rotations. Right? One physical rotation, it will take north, south, north, south. While here, one rotation takes only one magnetic cycle. North, south, north. Understood? So we can see that when we have more than 2 poles, or like 4 poles, something like that, then this changes the speed. So whenever we have 60 hertz, this will not produce 3,600. It will produce 1,800 RPM. Or this will produce 30 revolutions per second. It's no longer 60, because we have 2 magnetic rotation. Then this make an effect. So sometimes, as a shortcut, Nm, which is called the mechanical speed, which is the actual speed as well. This is related to number of poles. And we have the electrical speed, NE, electrical speed. This is related to frequency. So we can say that electrical speed is actually the frequency times 60. So at 60 hertz, it will be electrical speed 60 times 60, 3,600 RPM. So here, the electrical speed does not affect by the number of pulses, every time constant. How about the mechanical speed? The mechanical speed, it is frequency times 60 times 2 over number of poles, or in other words, 120 F divided by NP. NP here, number of poles. So at 60 hertz, the mechanical speed will be 120 times 60 divided by, here number of poles is 4, then it's going to be 1800 RPM. And this is the actual speed, which is the mechanical speed. While the electrical speed is related to the frequency, so which is related to when it is if we complete one rotation of magnetic and one rotation of electrical field, they will be the same. Which is when the number of poles here equal to, then we can say mechanical speed equals to 120 F over number of poles, then 120 times 60. Here is number of poles equal to, then the answer will be 3,600 RPM. So that one was the electrical, this one is the mechanical. So we can say that the electrical speed equals to the mechanical speed if and only if number of poles equal to. Otherwise, it will be different. So the mechanical speed will be less than the electrical speed. Okay, so these definitions, we need them. So those are very important to understand the topic. So we can see that we have two speeds definitions. The first definition related to the frequency or to the electrical parts. The second definition related to the mechanical parts. So the electrical parts has its speed, mechanical parts has its own speed. They can be equal if the number of poles is equal to 2, if we have only one magnet. When we have multiple magnets, this will matter. This will make the speed of the actual speed slower. So sometimes this can be as a benefit for us because we need to make the frequency, or we need to make the speed, the actual speed is less as the structure of the motor goes high, or as the motor, or as the generator gets larger, we need the speed to be less because the more speed, the higher vibrations will have. So we don't want this vibration to occur, so sometimes we prefer to have a higher number of poles to get lower speed. Worksheet number 12, it will tell you about the speed definitions. Now, there's some things called RPM, the speed, or sometimes in radian per second. So these are also very important definitions. The speed is still the speed, but what's the units? The mechanical engineers, they prefer an RPM. Or actually, this is what makes sense for us. I can imagine the speed 3,600 revolution per minute. I can know how high it is. But when I say the speed is 200 radian per second, okay, I know maybe 200 is higher than 50 or higher than 100, but I couldn't imagine how much that speed. But the electrical engineers, they used to prefer radian per second because it's related to the frequency. Because we know that omega equal 2 pi times F. So electrical engineers prefer to use this, while the mechanical engineers prefer to use RPM. Then we have N, revolution per second, while omega equal radian per second. So how to make the conversion? So you will see this in many questions, many examples in the textbook or in different parts, different words. You will see the speed in radian per second or the speed in RPM. So how can we make the conversion? So you need to know this formula. You can write this or memorize this. Radian per second equal 2 pi over 60 times RPM. Or we will make a shortcut. When we have the speed in radian per second, we will make it denoted by omega. When we have the speed in RPM, we will denote it by n. So we can know the difference. Some textbooks, they don't prefer, they use to denote the speed by n every time, but you need to look at the units, if the unit is RPM or radian per second. But I prefer my own way. I prefer to use n for RPM. I prefer to use omega for radian per second. Then radian per second equal 2 pi over 60 times RPM. Or in other words, omega equal 2 pi over 60 times n. How about the opposite? It can be found easily, which is 60 over 2 pi. N equal 60 over 2 pi times omega. So now we can recognize, or we can know that the speed can be RPM or it can be radian per second. Also, the speed can be electrical, can be mechanical. So you need to know these four definitions. You need to know the difference between them. So there is electrical speed in RPM. There is electrical speed in radian per second. There is mechanical speed in RPM. There is mechanical speed in radian per second. They are all speeds, but depending on the units, am I using RPM or radian per second? It looks like, am I using the distance in meters or in foot or in feet? So it's just like conversion. How about the mechanical and electrical? These are different things. The electrical related to the electrical parts, the mechanical related to the mechanical parts, or related to the actual. So the actual speed, again, is the mechanical speed. So here, this table summarizes. Sometimes here, let me call it N, let me call it NE, I don't prefer S here, M. So NE, the electrical speed, equal F times 60. This is in RPM because N in RPM. While omega E, the electrical speed, E for electrical, omega E, 2 pi times F. We know how to find omega, 2 pi times F. That's what we know. This is for electrical parts. How about the mechanical? The mechanical, 2 over number of poles times the electrical. So basically, find the electrical first, then 2 over number of poles. Here, for the omega, the same. 2 over number of poles times the electrical. So the first step, find the electrical first, then find the mechanical by multiplying 2 divided by number of poles. Then, when the number of poles equal 2, then the electrical equal to the mechanical. That's what we talked about. When we have only one magnet, which is who has 2 poles, then electrical equal to mechanical speed. This is the only way, otherwise there will be difference. Otherwise, every time the mechanical speed is higher than or lower than the electrical. The electrical speed every time is higher than the mechanical. And we need to be careful about something, which is number of poles. Number of poles, it must be even and integer. There is no way to have number of poles equal 1. There is no monopole in magnetics. So we cannot say we have only one pole, one south. No, for every south we need north, and vice versa. We cannot say we have 2 south, 1 north. No. So it must be integer and even integer. So number of poles can be 2, 4, 6, 8, 10, and so on. Number of poles. Clear? Any questions? Okay, so this worksheet is important for you to understand the differences in the speeds. Okay, let's go back to the notes and look here. When we have 2 poles, for 1 rotation, we have 1 voltage period. For 1 magnetic rotation. For 4 poles, 1 rotation, 2 voltage periods. That's what we talk about. So also these here, the formulas, also we talk about them. The omega, here omega, when I use omega, I mean radian per second equal 2 divided by number of poles times electrical. And in order to convert between RPM and revolution per second, then times 60. So just for your information, frequency, the unit is hertz. And hertz is actually 1 per second, or it's actually revolution per second. So whenever sometimes you see revolution per second, this is the same as the frequency. And also something else, sometimes we denote it revolution per second, since it's revolution per second, sometimes we denote it as RPS. Just for your information. When I say the frequency is 60 RPS, this means the same as the speed, or I'm sorry, the speed is 60 RPS, then I can say that the frequency is also 60 hertz or RPS. So again, the frequency here related to the speed every time. Then omega electrical equal to RPM times 2 over 2 pi divided by 60, number of poles. Okay? Sometimes the mechanical speed is denoted by R. In that worksheet, I denoted them by M. It doesn't matter. R means rotor. R, rotor. When we say omega R, rotor speed, which is the same as mechanical speed. So it doesn't matter. When you call it omega R, NR, omega M, NM, they are the same only for synchronous. When we go to induction, it will be something different, and we will talk about this later. But for synchronous, this is the same. Let's look at this example. A large 5,000 MVA. What does MVA mean? Mega volt ampere. And this means apparent power. Okay, so let me find that image. Is to be designed for a modern nuclear power plant in the United Kingdom. A steam turbine is chosen, which operates at efficiency 149 RPM. How many poles are recommended for that generator to design? The speed that we found the most efficiency at 1492 RPM. We need to calculate the frequency, or we need to calculate, the number of poles. Let's think about it. The first observation, we are in United Kingdom. What's the frequency?
50
hertz. And the efficiency, the speed right now, the actual speed that we need is 1492. Okay? We need to find, this is an RPM, of course, number of poles. Let's think about the formulas. We know that electrical speed equal frequency times 60. And we know the rotor speed, which is the same as the mechanical speed, equal 120 F over number of poles. Right? Do we know NR? Yes. Do we know F? Yes. What's the only unknown? Number of poles. Yes. So we can say that the frequency, or we need to find number of poles equals 120 F over NR. Or I think the opposites. The opposite, right? Is that right?
Yes.
Yes, I'm sorry. NP equal NR 120 F over NR. Okay, so 120 times 50 divided by 1492. How much the answer?
Oh,
Is it exactly 4?
that's 4.02.
4.02.
0, 2.
Okay. This is number of poles. But let's think about it. We said the number of poles must be even and integer. So what should we choose? What's the closest value? 4. Then choose 4. 4 poles. Okay? Clear? Any questions? Okay. Perfect. Now, let's talk about also this again. We need to convert this to take only the electrical parts. How can we model this motor? This is a 3-phase motor, so which is basically this will be converted from this. We'll first draw the equivalent circuit for the motor. Then that equivalent circuit, 3-phase equivalent circuit, will be converted from 3-phase to single phase by assuming it's balanced system. So we will assume the operation at balanced operation. Assume we are at balanced operation. Then we can convert 3-phase to single phase. That's why we have learned before 3-phase system, so we can find that at balanced system we can convert 3-phase to single phase. It can be applicable for any 3-phase system. So this is the equivalent circuits of the motor that's connected to the grid. EF is called electromotive force, and JXD, RA, these are related to the structure, the impedance, and the resistors, internal resistance of the generator. So why we have impedance? Because we have coils, and that coils, this produce a magnet, or we produce inductance. Every time when we have coils, this consumes inductance, and that cause means wires are rotating around a magnetic core or around a core, a ferrite magnet core. So this every time will have inductance. So that inductance, and we have a resistor, internal resistor, while EF is the energy that being produced by the moving parts with the magnetic field. Then points A and N are considered the terminals of the generator. Then this is connected to the grid. The grid can be, for example, Auburn University, can be Auburn City, etc. It can be anything. So as a shortcuts, we don't want to draw everything. As a shortcut, we used to shortcut everything to be voltage source and impedance. This is what's using what's to make a shortcuts to make use R Thevenins, V Thevenins. Do you remember this? So all of the utility grid can be converted to be R Thevenins and V Thevenins. So we will have, he will call it RG, VG, XG. So this using Thevenins. The derivation, you are not required to do this, but just for your information, using Thevenins. So we see that Thevenin's theorem also is very important for us. This is the generator inside the generator, and here is the grid using Thevenins. The grid, of course, is more complicated than that, but we make it as a shortcuts, as a voltage source and resistors, and impedance. In AC, it will be impedance instead of resistor. Now, can we make it? It's only single loop, but we can make a shortcut. Most likely, for strong grid conditions, these values will be small. So this can be negligible. We can neglect them if they are very small. And also, most likely, the internal resistance, if this generator is well designed, this will be small as well. Very small. So which means its impact is very, very little. So we can remove them, or we can neglect them. So we can make a simplified model by assuming the generator impedance is less, the grid impedance is very small. What it matters is only the generator impedance, and the resistor will be very small. So this will be negligible, this will be negligible. We will end up having this small circuit. It has only 3 components: EF, JXD, VA. And this is very simple circuit that can be applicable. Then can you imagine that we have modeled, where is that shape? We have modeled this large generator by only this simple circuit. This makes the life easier. So, the terminals of the generator are here, A and N. The grid, we assume only we have a voltage source. We assume the grid is very strong, then the grid impedance is low. This is just based on the assumption. And this assumption is valid for many cases. So when you are looking for maybe 95% accuracy or 98 accuracy, this is valid. But if your accuracy matters, then you need to go to the original model. But sometimes when we make some several analysis, we will find that this is enough. 98% accuracy can be enough for me. Then, these circuits, you need to either memorize this or not write this in your note sheets. So whenever I see three-phase motor, convert three-phase to single-phase, then this is the circuit associated with it. So after that, we can make our analysis. Most likely, EF is given from the data sheets. JXD can be given as well. Sometimes VA is given. Then you can find the currents. So when you have this, you can find how much power I'm generating, how much currents. When you have the current and you have the voltages, 3 times I conjugates, then you can know how much power being generated right now, right? So an example about the generator will be discussed next lecture. So next lecture I will talk about how to do analysis on this. So that's it for today. Thank you.